Good evening. Today I will be conducting your week 7 live session for the course of Computational Fluid Mechanics. So let's start. So we start by a question which we just um, started discussing in the last live session, which is related to solving simultaneous linear equations. So uh, So the question is, consider a system of linear algebraic non-homogeneous equation. So what is it referring to? It is referring to a system of equations like this. So x1 plus a1 to x2. Let's say there are n variables. So we have an equation like this. So it's linear. So this a11, a12, these are constant coefficients, and x1, x2, x3, and so on. These are variables. And this b1 in the right hand side indicates that this is a non-homogeneous equation. If this b1, if b1 equal to 0, then it would have been a homogeneous equation. So we are right now dealing with the non-homogeneous equation. And for a system of such linear non-homogeneous equation, we will have n equations for n unknowns. So since there are n unknowns, we would require n equations for each the system to be complete. So if we have such n equations, it will look like this. However, this still does not guarantee that the system is closed and will give us unique set of solutions. For that, we need to have certain other conditions which needs to be satisfied. So here we have the rank of coefficient matrix and rank of augmented matrix. So two matrices are mentioned here. One is the coefficient matrix. The coefficient matrix is nothing but the collection of the coefficients, the A's. So this, you can see that this produces a square matrix. So this square matrix is the coefficient matrix. It can be represented by this C, and its rank is given by R. So what does the rank say? The rank denotes the number of independent row vectors. So each of these row can be seen as a row vector, and any two rows, for example, can produce linear combination of any two rows can produce a number of other rows, and so on. Three rows can also produce other rows. So what we want to see is that how many independent row vectors are there. That is, no such row inside that in set of independent row vectors can be produced by the linear combination of other rows. That would mean that all the rows are independent row vectors. So if RC is the number of independent row vectors in this particular matrix, then RC is the rank of the matrix. What is the other way we can find out rank of a matrix? Is by performing row operations. So there are different kind of row operations that can be performed upon this. We had discussed that in previous session as well. So one thing that we can do is interchange two rows. Like first row and second row we can interchange. So we can call that operation as R12. The other operations that we can do is let's say R2, we are going to switch it, like R2 will be the old R2 plus some scalar multiplied by R1. So we can multiply a scalar to some other row and add it to the mm, another row, the row in question. And also, what else we can do? We can also simply multiply a scalar to a row. So R2 can be VR2. So this is the scalar. So these are the row operations that we can perform on a particular coefficient matrix. So these are basically like if you try to imagine we have a set of linear equations and we are trying to solve this linear equation by our like usual elimination method that we generally like have learned in school and so on. So the kind of operations that we will be performing on those set of equations actually corresponds to this row operations. So anything that we are permissible to do in such elimination methods is basically can be captured within these three row operations. And these three row operations are what is allowed for any kind of manipulation on this particular coefficient matrix. Now, with these row operations, if we can transform this matrix into an echelon form, row echelon form, where we might have, let me denote it by R. So R11, R12, and so on to R1n and Rnn here. So these diagonal terms will remain, and anything below the diagonal is zero. Anything below the diagonal is zero. So this is a upper triangular matrix form, or a row echelon form. So if like this kind of a form is there, what we do is count the number of non-zero rows. So it may so happen that like during these operations Rnn is decomposed into zero. So if it is zero, then our rank might be n minus one, provided the n minus one row is non-zero, and so on. So this is the way to find out the rank of a particular matrix. So RC is the rank of this coefficient matrix. What else is there? We are we have an augmented matrix as well. So augmented matrix is nothing but we add another column. So augmented matrix, we will simply add another column. So all these coefficients will be there, A11, A12, and so on, till ANN. So these are the this is the coefficient matrix plus another column of B. So B1, B2 till Bn. So this particular matrix, along with this uh, additional column, is known as the augmented matrix. So let's now see what is the question. So RC is the rank of coefficient matrix, RA is the rank of augmented matrix, and N is the number of variables. Now three statements are given. Solution is unique when RC is equal to RA is equal to N. Solution is inconsistent when RC is equal to RA less than N, and there exists infinite number of solutions when RC not equal to RA. So let's try to understand which one of them are true. So when RC is not equal to RA, what does that mean? That would mean that like so one thing we must understand that RA must always be equal or greater than RC. It can never happen that the number of rows in the coefficient matrix, non-zero rows, is greater than that of the augmented matrix, because augmented matrix will definitely like it is augmented matrix includes the coefficient matrix. So definitely, if there are some RC number of non-zero rows in coefficient matrix, in augmented matrix there will be RC or greater number of non-zero rows. So if RC not equal to RA, that means RA is greater. So if RA is greater, that means one equation has boiled down to left hand side being completely zero, whereas right hand side has a non-zero term. This is not physically possible. Like so, if that is the case, if RC is not equal to RA, then we must conclude that the system is inconsistent, that there is no solution possible. So RC not equal to RA will mean it is an inconsistent set of equations. So RC must be equal to RA for any consistency. Okay. Now what happens if RC is equal to RA is less than n? That is, number of equations is n. Since the number of variables is n, number of equations must be n. But when we try to find out rank, we observe that some of the equations are actually dependent on the others. So number of independent equations are actually less than n. If that is the case, then we must have infinite number of solutions. There will not be unique number of solutions possible because some solutions can be achieved as linear combinations of others. So if that is the case, we must have infinite number of solutions. So this will lead to infinite solutions. This corresponds to in our like 2D plane. This corresponds to like a set of lines which merge onto each other. So there are infinite number of solutions. What happens if RC is equal to RA is equal to n? So this is the ideal case scenario where when our rank is equal to the number of variables, and thus the number of independent equations is equal to the number of unknowns. So if that is the case, we will find a unique solution. So the solution is unique when RC is equal to RA is equal to R. So our first statement is correct. So if the first statement is correct, we have D as the correct option. Okay, let's move to the next question. So in the next question, we have to find the augmented matrix after forward elimination method. So forward elimination is basically like part of the Gaussian elimination process, which is basically the way we tend to solve system of linear equation using elimination method. That we will simply do with the help of a matrix form. The main aim of this particular process will be to convert the equations into this row echelon form, such that we can after this we can back substitute and find out the value of the variables. So let's do that. Let's first write the augmented matrix. 5 1 1 1 5 1 1 1 5. So this is the coefficient matrix. So I have written the coefficients of each of the unknown variables. After this, I will add another row which will correspond to the right hand side. So this is 8, 12, 8. So now let's perform row operations. So the first row will stay intact, and my first objective will be to make the other elements of the first column 0. So in a row of echelon form, always these elements will be 0. So let's start with the second row, how the second row would be manipulated. So the second row has 1, and I am trying to make it 0. So I have to multiply 1 by 5 with the first row and subtract it with the second row, and that would yield the first element as 0. So I have multiplied 1 by 5 and I will subtract it from 5. That would give me 4.8. This will give me 0.8. So 1 by 5 multiplied by 8 would give me 1.6. 12, if I subtract 1.6 from 12, that would give me 10.4. However, how about the last row? So the last row, I would have 0.8, 4.8, 6.4. Now what is the next step? The next step would be to make the second column of the third row 0. So now the second row also stays intact. Now this 0 will remain. This also becomes 0. So to make it 0, what I have to do is multiply 1 by 6 with the second row and subtract it with the third row. So 4.8 into 1 by 6 would be 0.8, and if I subtract it with the third row, that would make the second column 0. So 0.8 multiplied by 1 by 6, uh, 0.8 multiplied by 1 by 6 would yield uh, 0.133. So if I subtract, this would give me 4.67. Similarly, 10.4, if I divide it by 6, this would also give me 4.67. So, yes, so this will correspond to the option A. So I have successfully converted our equation to the form of upper triangular matrix with these elements as 0. You can see now how it will be very easy to solve the equation. So this basically means nothing but our equation has been reduced to this form. 4.8y plus 0.8z is equal to 10.4, and this is 4.67z is equal to 4.67. Notice how it is so easy to like solve now. We can find out z from the third equation. We can substitute that in the second equation, the value of z, and find out the value of y. And we can the value of y and z both can be substituted in the first equation to find out the value of x. So this is called back substitution. So we perform this forward elimination and then perform back substitution to find out the solution. This is called the Gaussian elimination. So option A is the correct one. So let's go to the next question. So system of linear equations is given here. We have to find the value of alpha for which the system has non-trivial solutions. So what do you mean by non-trivial solution? One thing that can be noted for this system of equations is that its right hand side are all zero. So this is a homogeneous set of equations. This is not inhomogeneous equations. So for homogeneous set of equations, the solution that exists is one solution that exists is a trivial solution. What is the trivial solution? Trivial solution is x is equal to y is equal to z is equal to 0. So if all these three are 0, then these equations are automatically satisfied, which is a trivial solution. So if there is only one solution of this particular set of equations, then the solution is bound to be a trivial one, because trivial solution is anyways a solution of this particular set of equations. So for it to have non-trivial solutions, it should imply that these particular like set of equations must have infinitely many solutions. So if it is just one unique solution, which is RC is equal to RA is equal to N, if that is the particular condition that we apply, we arrive at, then it will give us only the trivial solution. If we want non-trivial solutions for this set of equations, we must have that RC equal to RA, which is less than N. So for that particular equation, for that particular condition, particular condition is generally used is that determinant of the coefficient matrix must be 0. You can also like follow a longer route by calculating the rank of the matrix and what should be the case here? The case should be that the rank should be 2. Rank should not be 3. So that is also one way in which this particular uh, solution can be approached, and that is also not a very difficult solution here. So if you just write the coefficient matrix, so this is 1, this is 1 plus alpha 1, 6, 4 alpha plus 1, 3, 1, 4, 1. If you perform row operation here, so you can easily put this as 0. So you have multiplied 6 and subtracted here. So if 6 is multiplied and subtracted, then you will have minus 2 alpha and minus 5, minus 3 here, and here this can be simply subtracted. So 0, 3 minus alpha and 0. So you can clearly see for this to have a rank of 2, what you must have alpha minus 3 equal to 0. So that gives you the value of 3. So this is a way that it can be done. Another way, as we said beforehand, that a determinant of the coefficient matrix must be 0. So we can calculate the determinant as well. 4 alpha plus 1, 1 plus alpha. So this must be equal to 0. So This is 4 alpha plus 1 minus 12 minus 1 plus alpha. This is 6 minus 3. Okay. Plus 24 minus 4 alpha minus 1. This is equal to 0. So you can calculate how much this will be. Minus 3 alpha plus 9 equal to 0. So yes, you can find out here as well. Alpha is equal to 3. Okay. So let's move to the next question. So in Gaussian elimination technique, the technique that we have been discussing right now, which process is rate determining, and what is the order for the uh, steps involved. So what is the rate determining step? Rate determining step is the step which takes the maximum number of numerical operations or the maximum effort. So there are mainly two operations here, what we had discussed. One is the forward elimination. What is forward elimination? It is the a process by which we convert the coefficient or the augmented matrix into a row echelon form, into the upper triangular matrix. And then next is back substitution, backward substitution. This is basically the step in which we find out the value of the variables by substituting from the last equation and to the second last and so on. That's why it's called the back substitution. So which one is the rate determining step? Forward elimination is the rate determining step because that takes the maximum number of operations. So forward elimination, now we have to determine the order. So the how many operations are to be performed? So one operation that let's take an example. Let's take an example. So here we had performed this operation. So what is the number of operations? So one, firstly, I have to find out what I have to subtract from the let's say from the second row. What I have to subtract. So I had multiplied 1 by 5. So that I found out by dividing 1 with this 5. So 1 by 5. So that is one operation. And this operation I have to perform for the all the number of rows. So this can be this is total n operations. After that, I need to subtract the whole row with each of these rows. So that is n into n. So I have to first multiply uh, the 1 by 5. I have to multiply with each element, and then I have to subtract each element with this row. So n for the multiplication and n for the subtraction. So total, I have 3n n cube number of operations for this whole process. So it will be n cube order. So forward elimination and n cube. This will be the answer. If there is any question, you may ask. Let's go to the next question. So the next question is like states that if like during Gaussian elimination we have division by zero. So division by zero during back substitution part of Gaussian elimination. What does this imply? When can we have division by zero? So if we have already, suppose we have performed our uh, forward elimination. So if we have performed forward elimination, then we have already obtained this form where these are all zero and uh, this an is there, and now we are performing this back substitution step. So in this back substitution step, what will be our xn? Xn will be is bn divided by an, and then we will substitute this xn to the second last equation and then find out xn minus 1. So it will be some bn minus 1 minus some a n minus 1 comma n x xn divided by a n minus 1 comma n minus 1. So you can see like we are always dividing by the diagonal elements to find out the unknown variables. So division by zero is only possible in this particular step when your diagonal element will be zero. If any of this diagonal element is zero, then I will have a division by zero error. So which option will be correct here? The option A will be is the correct option here. So if diagonal coefficient in the triangular matrix, any element of this diagonal is zero, then I will have a division by zero. So next question is of LU decomposition. So LU decomposition is a different method. LU decomposition, what we have, if we have a coefficient matrix A, then we decompose it into two matrices, product of two matrices L and U. What is L? L is lower triangular matrix. So here all the lower triangular elements, these are non-zero. Upper triangle is completely zero, and U is the opposite. U is upper triangular matrix, like the row echelon form that we were doing. So here we simply decompose into these two and then try to find the solution. So it is like from Gauss elimination only we saw that the like handling such like triangular matrices are much easier. So that's why here we first like in the first step itself we decompose it into L and U. So this is LU factorization. So A is the coefficient matrix that is decomposed into L and U, and then it is solved. The equation is solved. So LU decomposition was developed keeping in mind that Gaussian elimination is difficult to implement. Is that true? So Gaussian elimination is the basic elimination method that we do. Like even like before we have learned like the formal way how to do a Gaussian elimination method. When we are given a set of linear equations, what we generally do is the elimination, which is which resembles that of the Gaussian elimination method. So Gaussian elimination method is very like simple to implement. So this statement is not correct. So His statement is not correct. Gaussian elimination is the simplest method that we can use. However, it is very uh, computationally expensive. It requires that forward elimination, which we saw is like n cube number of operations. So, what is the second option? Dealing with triangular matrices is advantageous, which is true. This is true, as we like just now discussed. Like triangular matrices are very easy to deal with. So this is correct. Reduction of the number of calculation by an order of the number of variables is guaranteed compared to Gaussian elimination method. Is this true? This is not true. As we will see that LU decomposition, this like factorization also takes n cube number of steps. So there is really no reduction in number of calculations in this particular method. However, like if this uh, like if the this LU decomposition in some particular cases is very like easy to obtain. So if LU decomposition is easy to obtain, then it will give us a advantage in computation. Otherwise, this for a generic matrix, decomposition into L and U itself takes a significant amount of computation. So only advantage is dealing with triangular matrices. So 2 only will be the correct option. So what is rate determining step in LU decomposition? It is the LU factorization. So when we break this A into L and U, this step is the rate determining step, and as like just now we like discussed that this is also an n cube operation. So here also we have n cube number of operations uh, the for this step. So here this will be the answer. So rate determining step is LU factorization. Backward elimination and back substitution, these are of Gaussian elimination. That is not for the LU decomposition method. LU factorization is LU decomposition method, uh, and this number of operation is still n. So another question related to LU decomposition. So it is asking when is it faster or when it is not faster compared to Gaussian. So is it always faster than Gaussian elimination? It is not like faster. The number of steps required for this particular method is the same. So it is not always faster. When is it faster? So it is faster than Gaussian elimination only when coefficient A does not change. So if matrix A in this LU decomposition like remains the same, so A is either L or U. So in such a case, the other matrix will be an identity matrix. Or there is a very like clever way of decomposing this A into L and U. So in those cases, this matrix, this elimination will be faster. So when A coefficient A will not change, then definitely Gaussian it will be faster than Gaussian elimination. Option 3 is this is faster than Gaussian elimination only when augmented matrix does not change. Now this factorization step This is the rate limiting step. This actually does not depend on our augmented matrix. So it only depends on our coefficient matrix. So, so option 2 will be the correct option. Okay. So let's try to answer this question. Next question. So here a system of equation is given, and we are trying to solve this using Gaussian elimination method. What is special about this particular system of equation? That epsilon is a very small number. So Gaussian elimination successfully solves this system of equation as it is. This is the first option. Second option is Gaussian elimination is successful in solving this system of equations after reordering of the equations. So why is a reorder necessary? Why is this asking for a reordering of the equations? So what does this epsilon change in the way we are solving this equation? So what are the steps which is required for this Gaussian elimination?
Two and three.
2 and 3. Why can you explain?
Gaussian successful when epsilon tends to 0.
Yes.
When we divide it uh, during forward elimination, it will tends to infinity term, the second
Yes.
term.
So
So,
the a small number is very difficult to divide.
hmm,
So uh, so if we have a small number and that is in the diagonal,
hmm,
if it is in the diagonal, then we will need to divide it. Not only in the forward elimination method when we are like trying to eliminate other rows, but also in the back substitution method, we will need to find out the unknown variables by dividing epsilon. So
hmm,
what we will generally want to do, we would want this epsilon to be in an off diagonal term.
hmm,
So if we can simply rearrange these rows in such a way. Let's first write the first equation and then write the second equation. Now we have avoided the problem. In our coefficient matrix, this epsilon is now in an off diagonal term. So this is the diagonal, and epsilon is in an off diagonal. So that's what we want to do. So Gaussian elimination is successful in solving this equation after reordering of the equation. So reordering is necessary. And what is the third? Diagonal elements in the coefficient matrix must be preferably be the greatest compared to other coefficient of the same row. And which this is true. So for Gaussian elimination to work very smoothly, we would want the diagonal elements to be larger. First and last column terms for all rows in the coefficient matrix must be large. This is not true. First and last column terms are not nothing special. Diagonal elements, however, hold a special position in Gaussian elimination. So, as you said, 2 and 3 is the correct option. All right. So like we have covered Gaussian elimination and LU decomposition mainly till now. So next we would move to like finding norms of vectors and matrices. So what is the second norm? We have to find here second norm and first infinity. So can you tell me what is the like second norm of a matrix?
So, sir,
Yes.
what about tridiagonal matrix algorithm?
Tridiagonal matrix algorithm is there. No? Can you tell me which what is there in that portion?
Tridiagonal.
What is there in that portion? Am I missing some portion that has is there in this problem in your syllabus?
Yeah.
Okay, okay. Like tell me which portion is this?
Usually, of the algorithm complexity reducing to the order of n,
Hmm.
uh, by considering only the diagonal and the row, just three diagonal up,
Okay,
just
okay.
above diagonal and
I think I can understand what you're trying to say.
okay, okay.
Uh,
So I have a doubt in that. Actually, what is backward elimination means?
Backward elimination.
Uh,
So I like if I understand correctly, you're talking about. Let me write it here. So if we are trying to say like if there are three diagonals, like
three
uh,
diagonals.
so A11, A12, like this is there,
Uh,
and you
Immediate diagonal
and you
above and
have
below.
yes, you have this uh, here, and you have another diagonal this side, right? Okay. Can you tell me what is your like doubt in this?
So during the algorithm, what the backward elimination step means in assignment, it was asking what backward elimination algorithm. We have studied only forward elimination and backward substitution, right?
Hmm.
So I want to clear whether the question is not correct, or is there any term backward elimination?
Okay. Can you like share the question? Then it will be very uh, like easy for me to discuss. I do not have assignment question for you. This assignment has already been submitted, I guess. Right. The date is over, so I can discuss. Right. So week 7 assignment. Right. This is.
It's week 7 assignment.
No. So if the date is still there, then I am not allowed to discuss right now. Okay, the assignment question. Actually, the
Uh,
best thing will be like let me try to find out a question for this diagonal matrix. The assignment that I had been given to discuss it did not contain this. So not a problem. I will means give anyway I give a 5 minutes break in the middle. So I will try to find the question for this and then discuss it. Okay.
Okay, so I don't
Hmm.
want to discuss the question. I want to make the clear what is backward elimination step.
Okay. No
That's
problem.
only
No.
third question in assignment 7.
Okay. Okay. So let's do one thing. Let's take a 5 minutes break and then we can continue. All right.
Okay, sir.
Hmm.
Okay.
Okay. Hello. Yeah.
Hi.
Am I audible? Can you see my screen?
Yeah.
Okay. So I couldn't find anything with the diagonal matrix in the assignment. So I do not have any question to discuss with you. But like let us discuss the like tridiagonal algorithm.
Okay.
So if we have a matrix like this, so let's just simply name this like A1, A2, AN, and let's say we have B1, B2 till this will be till Bn minus 1, and similarly from C1, C2, this will be Cn minus 1, right? And the other elements are 0. This is the structure of the uh, tridiagonal matrix, and this is multiplied with our unknown vector, and there will be a inhomogeneous term. So we can have this x1, x2 in variables, and let's say b1, b2. So the way this is solved is very similar to Gaussian elimination. So in Gaussian elimination, what we do, we have like we do not means it is not a sparse matrix. So what is a sparse matrix? Sparse matrix is any matrix where most of the elements are 0. So tridiagonal is an example of a sparse matrix where most elements are 0. Only the like diagonal or the near the diagonal the elements there are non-zero elements. So sparse matrices are generally easier to solve. Uh, so here we will perform the same Gaussian elimination method, but just we will not be needing to like convert this into a completely upper diagonal matrix in the same painstaking way. Why? We only need to convert this only this one particular element into zero. So this particular element we need to convert it to zero. So we will perform the row operation in the same way. So here what we will need to do, we will need to multiply b1 with the first row and subtract it. So that will render this b1 as 0. So similarly, this b2 element, this we will perform a row operation. So for this whole thing, the number of row operations that we will need is just n instead of n cube. The number of row operations is drastically reducing because we need not to like subtract the first row with the third, fourth, and so on. We just need to subtract the first row with the second row, and similarly the second row from the third row. And this is the way we will go. So here also there are two like processes that you were saying. Uh, there is forward elimination, which is the process of converting this into a upper triangular matrix. And then there is the backward substitution, which is again like when we like complete the forward elimination, what we will have, the last row will only have some coefficient multiplied with xn is equal to something on the right hand side. So that would easily help us to calculate xn, and then xn can be substituted in the second last equation to find out xn minus 1 and so on. So that is the back substitution method. So this is what is performed. So this is basically nothing but Gaussian elimination, where the coefficient matrix allows us allows the whole process to be much quicker.
Okay, sir. But
Yes. Hmm.
in the assignment, it was written as what will be the backward elimination algorithm for the computer code.
Mm,
I don't understand what they mean
de
backward.
yeah, depending on the question, they might either mean backward substitution, or if means you can also read the question in the way that uh, if there is forward elimination, you perform backward substitution. It might also, I don't, since I don't know the question, I cannot really say, but it might also mean that they are trying to perform some backward elimination and then forward substitution. You can understand, right? That also can be performed, like
Backward elimination and
a forward substitution, like basically the opposite of this process. Here, like if we try to convert it into a, let's say, a lower triangular matrix. Like for example, Cn, if we try to make it 0 using row operations, right? If we try to make Cn minus 1 0 and so on, then we would do a backward elimination and then reach row number 1, and from row number 1 we will try we would be substituting. So row number 1 we will reach, we will find out x1, then x1 we will substitute in the second equation, find out x2 and so on. So
okay.
basically the opposite method of the conventional Gaussian style.
Okay.
So depending on what the question is, it might either mean like back substitution itself, or it might mean like the one that I said.
Okay, sir.
Because in this method, it is really means there is no hard and fast regulation that we have to substitute in one direction and eliminate in the other. We can always do the other way around as well.
Okay.
Okay. Is there any other method that is like not there, and you want to discuss that also? You can tell me, because I do not have the like syllabus as I have few past year assignments and all. So
No.
this year I am trying to understand. Okay.
Now, now norms we have to start, I think.
Okay, now we have to start. So let's discuss the uh, yes. So second, so the question here is find the second and infinity norm for the particular vector. So what is the second norm? The second norm is basically the Euclidean distance that we do. So squaring and root over.
Root.
So how much that would be? 3 square 9 plus 4 plus 25 plus 40. So this is 87, right? Root over 87. And what about the infinity norm? What is infinity norm? So infinity norm is nothing but the in this
X
particular,
max.
yes, this
XI
will
max.
be the maximum version. So that is 7 in this case. So this will be the fact. So what is norm anyways? So norm is basically a way of like trying to gauge the magnitude of a particular vector or matrix. So matrix and vectors, these are collection of numbers. So really like uh, we should have a way to measure how much big a matrix or how much big a vector is. So there are different types of definitions that we can use. So those are basically norms. So norms must be positive, and it has some certain other like kind of rules and regulations. So if a scalar is multiplied, then norm is basically multiplied with a particular scalar as well. And also we have that vector addition um property with like two a plus b. Uh, A plus b norm is there. This will be less than equal to a norm plus b norm. So these properties are there, which like every norm must like follow, and we have like different definition for like norms. So here is another statement. So is this correct? So the first statement is not correct actually. So the norm is denoted by like this. So actually the second statement will be correct. So the second statement gives us that this is greater than equal to any such matrix. So this is a more generic statement which is correct. So like this will you can see very clearly that this particular statement is a very special case. So norm is not given by this. Whereas this is correct. So if k is multiplied with a matrix and you want to find out the norm is also multiplied by this particular scale. So 2 and 3. Okay. So uh, what is the first norm and what is the infinity norm of this particular matrix? So what is first and what is the infinity norm? The definitions we must like know to solve this particular question. So what is the definitions? So for infinity norm, we like did for a vector. Uh, yes, please.
Uh, First norm means maximum of the row, sum of rows.
Hmm. First norm is maximum for the row sum,
Rows.
right?
Yeah. Infinity means maximum of the column. Sorry, first norm means maximum
I
of
think
the
you have,
column norm.
yeah, yes, yes.
Column
I
norm,
think
and
yes,
the infinity means maximum of the row norm.
yes. So first norm will be a maximum of a column sum,
So,
right? So
mm,
we have you take and each of these sums that we are talking about absolute sums. So if suppose there was minus 3, we would have taken like mod of minus 3.
more.
So 3 would have taken. So let's like for the column sums, we would do like this. And we would take the maximum of it. So let's like calculate. So first now we will add up the columns. We would add up the columns. So this is 12, this is 13, and this is 20. So 20 is the maximum. So 20 is the first one. So 20 here and here are there. 20 is the first norm. And what about the second infinity norm? Infinity norm is 6 plus 3 here is 9, this is 14, and this is 22. So 22 is the highest. So 22 and 20. So first norm is 20 and infinity norm is 22. So this is the fact. All right. So these are there, and yes. So the next portion that is there is the uh, iterative methods for finding out this system of linear equations. So Jacobi and
So,
Gauss-Seidel. Yes. Yes.
can you give an example of second norm, finding second norm for a matrix?
Finding second norm for a matrix. Uh, See the formulas. The second norm is nothing but is the idea behind second norm is the inner product.
Mm.
So like inner product you take and the square root. So you can find the like you will get the definitions.
Yes, sir.
So second norm of a
Is
matrix.
there any condition for selecting the maximum value for x or something? We
Sorry.
are considering an x matrix, right?
Yes.
Column. In that, if we find out the values for x, is there any condition for selecting the maximum value of x?
In the second norm you are talking.
Yeah.
Uh, I have to see. Like it's generally like we take the I guess we take the Euclidean distances for the uh, vectors, right? In this,
Mm. Uh, for a matrix, we will consider a form like ax is equal to b, where
hmm.
the norm of ax divided by norm of x we have to find.
Okay. Like you see the formulas. I will means there are different kinds of like formulas that you can like get for this.
Second norm.
Yes. Hmm. So, like more important is the like the idea behind this. So the
Mm.
idea is based on Euclidean distance. So second
Mm.
norm is very important and is used for a lot of cases. And the idea is like means to find the like Euclidean distances. So,
Mm.
like vector wise, you can find it, and then we like I think we have to find the maximum of the means in the inner product. You have to find the maximum or something like that.
Mm-mm.
You
If
can
we get
like
a maximum value of that x, if there is condition for selecting the values for x, that's my doubt.
I would have to like check and see.
Okay.
Okay. Uh, Means the definitions are there. Definitely, you can like check it out. But
Mm.
means it is uh, I cannot like recall on the top of my head.
Okay.
Uh, like best thing like if you are using a software like MATLAB or well, Octave, uh, best thing will be you can check it from there. Those are like matrix libraries itself.
Okay.
So they would have the best definitions available for your finding the PF now.
Okay.
Okay. Uh, any other question you have?
No, sir.
Okay. So yes. So like, can you tell me like the Jacobi and Gauss-Seidel? What is the difference between these two?
Jacobian, we are initially guessing x1 and x2,
Yes,
and this x1 and this x2 is substituted for the next iteration.
yes,
For Gauss seidel, we will find out x1, and this x1 is substituted to find out x2.
yes. That's right. So in Jacobi, like both of them are iterative methods. So iterative
Hmm.
methods, we take an initial guess, which is written here. So this initial guess we will take, and using this initial guess, we will update our guesses. So we will substitute in both this equation. So generally, like the first equation is taken as for the x1, and the second equation is for x2. So our next x1 guess will be 10 minus x2 by 2. So x2 here is 0, so this will be 5. And for our Jacobi, we will not update our x1 based on our first value. So here x1 is still 0. So whatever the x2 we will find, which will be 11 minus x1 by 2. So this will x1 will still be 0, and my value will be 5.5. However, if we were using Gauss seidel, we would use the values that we have found for x1 in our calculation of x2. So, so it will be 11 minus x1, which is 5 in this case. So 6 divided by 2, it will be 3. This is the difference between Jacobi and Gauss. And like in subsequent iterations also, Jacobi updates all the values at once, whereas Gauss seidel keeps on updating its values based on each equation that we are solving. Okay, so here it is like asked to find the value of x1 at the end of 3 iteration step. So you can do this. So first step, let's first do Jacobi. So in the first iteration, uh, x1 and x2 were 0. So in the first iteration, x1 will be 5 and x2 will be 5.5. The second iteration, x1 will be, so x2 is 5.5. So x1 will be 4.5 by 2. So 4.5 by 2 will be 2.25. Whereas x2 is, so this was 5, so 6, this will be 3. In the third iteration, x2 is 3, so x2 is 3, so this is 7 divided by 2, this is 3.5. Whereas x1 is 2.25. So x1 is 2.25. So this is 8.75 divided by 2, 4. So this is Jacobi. And we can do the same with Gauss. Gauss, this is 5, but after that it will change. So x1 is already 5, so this is 6, and this is 3. In the second iteration, This we will use x2 is equal to 3, so that becomes this 3.5. Now we will again use 3.5 as our guess for x1. So we use 3.5. This becomes 7.5 divided by 2. This becomes 7. That is the third iteration. 6.25 divided by 2. 6.25 divided by 2 will give us 3.125. And 3.125 if we substitute here, we would get so 7.875 divided by 2. 7.875 divided by 2 will be 3.9375. So somewhere like this. So you can definitely see Gauss-Seidel is converging much faster than compared to Jacobi, as is expected. So our answer here will be A, 3.5, 3.1, 125 for value of x1. Let's. So this was the last question that was to be discussed in this particular week. If there is any question, you can ask. Otherwise, we will continue in the next session, which will be in the next week. This time. Is there any question?
No, sir. It's clear.
Thanks for joining. I'm stopping the recording.
Okay, sir. Thank you.